Our sole purpose today is to cover the Chapter 17 review problems. We're going to work from both version 1 and version 2. And to begin with, so I wouldn't have to stumble around with my equations, I put the important equations that we're going to use up here if needed. All right, so the first one I have highlighted is number 9, I think. Chapter 17, version 1, review document number 9. The reason I put this one in here, and 10 also, is that at 1 atmosphere and 100 degrees, we would expect water to be boiling. And that would be an equilibrium situation where delta G is 0. But under certain circumstances, at 1 atmosphere, water can be heated above 100 degrees. It's a process that doesn't last very long, but in that hypothetical situation, if it's above 100 degrees, then we're no longer at equilibrium. Okay. So the question here is, if we are at 1 atmosphere and the liquid water is heated above 100, what is delta S for the surroundings? Is it less than 0, equal to 0, greater than 0? Well, actually, delta S for the surroundings would be a value. And then remember, if we add the delta S for the system, right, at equilibrium, that value is 0. So they're going to be equal to one another. But in this case, when we add more energy, let's draw a picture, right? Here's our surroundings, and there's the system. And so this is our water that we're trying to heat. And if we add more energy, right, if we add Q to that one, then we are adding energy entropy. We're increasing the entropy here above that for the system, above that for the surroundings. Let's see. The entropy for, if we're adding heat, it has to come from the surroundings, right? The heat has to come from the surroundings to enter the system, which means the heat is going to be a positive value. And if we look at this one over here, delta S for the surroundings is equal to negative enthalpy. And if the pressure doesn't change, right, its process is at constant pressure, then this is also equal to Q. Remember that discussion. All right, so if the surroundings are losing heat, the Q for the system is plus, so the Q for the surroundings must be negative. Am I doing this right? No. That delta H is relative to the system. Excuse me. This is system. So if this value is positive, then the overall value is negative. And that means the delta S for the surroundings would be negative. So that means as we're increasing the entropy of the system, we're decreasing the entropy of the surroundings. Okay. I hope I didn't confuse anybody with that one. Okay, so 10 uses the same situation. And now what we're looking at is what's the delta S for the universe. So this would be the delta S for the universe. when we add the surroundings and system. And the universe here, like I said earlier, in this case where we're actually identifying a limited surroundings, this would be better written as total. Like, what is the delta S total? All right, so if we're at equilibrium, then this value would be 0, because that would have to equal that. Okay, but we're saying that at 100 degrees and 1 atmosphere of pressure, we're actually increasing the temperature for the system. And that means the entropy of the system is increasing above what the surroundings is losing. Okay, so that means this is going to be greater. We would say delta S, write that better. Delta S for the system under these circumstances is greater than the delta S for the surroundings. Okay, in that case, and this is, I probably should say that, absolute value. So the amount that the system is getting is greater than that the surroundings is losing, and that makes this value positive, greater than 0. Okay, everybody's kind of okay. All right, let's move on before I lose you. All right, so let's scroll to the next one. And I think it's quite a big, no, we got 11, and then we're going to get a big jump. Okay, so there's 11. All right. So which of the following is true? None of the E is none of the above is true. So that means we've got to go through every one of them and logically determine truth or falsehood for each one. So A, B, C, D, and then of course E is none. All right, let's see. What do these statements have in common is by spontaneous we mean. That's the beginning of every phrase. So we're talking about conditions that promote spontaneity of a reaction. So by spontaneous we mean. So let's see if we can, by process of elimination, get rid of the ones that cannot possibly be true and see what we got left over. How about spontaneous A? By spontaneous, we mean that the reaction in the process will always proceed to the right as written. Yeah, as we write it, left to right means we're saying that's spontaneous. So that part is true, even if very slowly, because we're talking about thermodynamics here. We're not talking about kinetics. It may take a long time for it to happen, but eventually it's spontaneous in left to right. Increasing, okay, now we're going to say something else about it. Increasing the temperature may speed up the reaction, but it does not affect the spontaneity of the reaction. Okay, that's possible. So we'll say this one's possible. How about B? By spontaneous, we mean that the reaction or process will always proceed to the left. Okay, that one's out. Going to the left is not spontaneous by our convention. Going to the right is spontaneous. Okay, do we have another one that's to the left? Yeah, C. C says to the left also, so we can cross that one out. How about D? By spontaneous, always proceed to the right. Okay, so that one's good up to that point. Let's see what else we got going for us here. Increasing the temperature may speed up the reaction, which is the same statement as A so far. And it generally affects the spontaneity of the reaction. Okay. A says does not affect the spontaneity of the reaction. Temperature change does not affect the spontaneity of the reaction. D says it does. So that's the difference. temperature is the question mark. Right? Does it affect? Let's see. Does it not affect? Temperature not affect spontaneity? Or temperature does affect? Okay, so how do we get a handle on this? I think the easiest way is to look at this equation right here. Right? We know that if delta G is negative, that's spontaneous. Okay, that's also equal to delta H minus T delta S. Okay. If we change the temperature, we change this whole term here, which changes G. Right? So temperature does have an effect on spontaneity. Right? So that gives us D. D is the correct answer out of all those. And since we found one that was true, E is can't be true. Well, right. Now I think we have a big jump into the 30s. Let me see if I can get there quicker. How about this? Yeah, there we go. And 38, too far. There we go. 34. For the following reaction, carbon dioxide, water, that's a gas, and water's a gas in this one. And we need two of them. And that's an equilibrium with methane and oxygen. Okay, and the delta H0, the standard conditions enthalpy, is positive 803 kilojoules. Which of the following will increase K? All right. I think this is one that has two possible solutions. The easy way and the hard way. Yeah. All right, let's do the easy way first. In fact, we can solve this with what we learned during equilibrium. If this is a positive value, where does this fit in the equation? Right? It's an endothermic equation, right? So that means delta H fits over here on the reactant side. We're putting heat into it. All right. So, which of the following will increase K? Well, what's the K expression? Well, the K has methane here, has oxygen here, square. It has carbon dioxide here, and it has water. All these terms are valid. Right? So if we, let's say, just for argument's sake, we increase the temperature. If we increase the temperature, we're adding heat to this side, which drives the reaction this way, makes these terms bigger and these terms smaller. So increasing temperature would increase K, right? Increasing temperature increases K. Is that one of our choices? Increase the temperature of the system would increase K. C would answer that question. Now that's the easy way. That's the Le Chatelier's way. The other way looks at this equation right here. So if we were to draw this, and this will be our X term, 1 over T, should be Kelvin to the -1, and this one will be log of the K. And it's going to have a negative slope. And let's see, what else do I need in here? Okay, that's all we needed. So if we increase the temperature, if we increase this value, what does it do to this term? It decreases it, right? So if we increase the temperature, instead of going that way, it's going to go back this way. Make this bigger, then it makes that term smaller. So it's going to move this way as we increase the temperature, which means this value increases here. And if the log K increases, K has to increase also. So that's the chapter 17 version of the solution. Okay, 34. That's that. Oh, before I forget it. Here. Okay, 34, 36. Okay, 36. I think this one is also, we can solve this one with Le Chatelier. If we have this gas phase reaction, NO, nitrogen monoxide, these are all gases. 1/2 oxygen is in equilibrium with NO2. And the standard enthalpy is minus 5691 kilojoules. And the equilibrium constant for this is 1.46 times 10 to the 10 to the 6th. So that's way to the right. At 25. Okay. This means at 25 degrees. That's standard temperature. And of course, standard pressure also 1 atmosphere. Okay, what would be the effect on the amount of NO present of compressing the equilibrium system to a smaller volume? I think the best way, and keep the temperature constant. Don't change the temperature. We only change the volume. Okay, so we can use Le Chatelier here. In fact, we don't even need this value to answer that question. How many moles do you have on this side of gas? Right, all these are gases. Well, you have 1.5, right? 1.5 moles. And over here you have 1 mole. So if you compress, you decrease the volume. You're increasing the pressure. And which way is it going to respond? It's going to go right. It's going to relieve some of that stress by making fewer moles of gas. Right? So if it's going to go that direction, I think we can probably answer the question now. The amount of NO will increase. Nope. NO will decrease. B. And the answer doesn't depend on K. Okay. If it's at equilibrium and we do something to it, it doesn't matter what K is. K is the same no matter what you do to it, except for temperature, of course. Okay, so that was fairly simple. All right, let's see. Keep going. Here we go. 46. Yeah, 46. We want to calculate the normal boiling point for formic acid. So what's the boiling point? for, let's see, H. We write formic acid this way. This is kind of like the acetic acid type that I showed you earlier. We can write it this way, or we could write it CH2O2. That would be formic acid. But this way of writing it tells us that's the acidic hydrogen right there. No, excuse me, that's not. This is the acidic hydrogen right here. Because if you write it like this, we know that's the acidic hydrogen. That's the only reason it's written that way. But that's immaterial for what we want. The boiling point for this one. So the process is going from this liquid to this gas. There we go. And we're given different values. We're given the heats of formation, and we're also given the enthalpies. And the question is, what's the normal boiling point? All right. What we can say is at the normal boiling point, the enthalpy of the surroundings is equal to the enthalpy of the system. Because delta S total has to be 0 at the boiling point. Assuming we're at the boiling point and we're not doing like we did before and increasing it above the boiling point. It's at the boiling point. That means the delta S surroundings has to be equal in magnitude and opposite in sign to the delta S for the system. So the delta S for the system for an equilibrium situation is just this value with the opposite sign. Okay. All right. So in order to find the boiling point, and now since this is the equilibrium, then we can solve for this one. If we can find delta H and delta S for the system. Okay. So the delta H for this situation would be what? It would be delta H for that minus delta H for this. So for the gas is minus 363 kilojoules per mole, and there's only 1 mole of each. And then we have to subtract the enthalpy for the liquid, minus 410. So minus 410 kilojoules is equal to what? Let's see, that's it's a positive 7, 6, 4, yeah, plus 47 kilojoules for delta H. How about the entropy? Entropy, we would do entropy for the gas, 251.1. This is joules. I got to keep track of that value. Minus for the minus 1/3, right? 51 minus 130 joules. So this would be, let's see, 0.1. 1, 1, 2, 1, right? Joules. Okay. Now, if we want to solve this one for temperature, right, we take that one and solve it for temperature. That would simply be delta H over delta S. But we need common units of measure. Right? So 45 kilojoules would be equal to 47 times 10 to the 3rd joules, right? So it'd be 4.7 times 10 to the 4th joules. So now we can put these values in here. 4.7 times 10 to the fourth joules. Well, actually, this is joules per K. Isn't it? Yeah, joules per K. We already multiplied the moles out of it by 1 and 1. So the moles are gone and we still have joules and K left over. So this is 121.1 joules per K, and the joules cancel, leave us with K, right? The denominator of the denominator is the numerator, so that comes up here. So I just need to do some little calculation here. Yep, 121.1. So this is, let's see. I think I rounded off to 388 K, but our answer's in C, correct? So we have to subtract 273. That's 5 and 1. 115. 115 degrees C. Okay. No objections? All right, we'll move on. That's 46. Doing enough time, okay. Let's see. Skip a few. 52. All right, there's 52. Let's see. 53. Okay, we'll go back. Check 52. All right. We want to calculate the delta G for this composite reaction, and we're given two other reactions that we can combine to make that first one. I think that's the objective here. So we're looking for delta G 0 of this reaction. Water, gas, plus 1/2 oxygen gas yields hydrogen peroxide gas. Okay, and the temperature is 600.1 K. Okay, all right, we've got this other information. All right, how are we going to find delta G 0? Well, we have delta G 0 here. We got it here. We don't have delta G. We don't have delta ST. I think we need to focus on this one, because if you look at the information given, you're given equilibrium constants for those individual equations, and we can composite those into this one using Hess's law and determine what the K is from this reaction out of those two. Okay, so the first reaction has hydrogen, oxygen, and hydrogen peroxide. Okay, that one's good. It's got oxygen on one side, it's got hydrogen peroxide on the other side. Okay. So we can take this one, H2 plus O2 and hydrogen peroxide. Right. And the K for this one, let's put up here. The K for this one is 2.3 times 10 to the 6. Yes. 3 times 10 to the 6. Okay, that got us this term. It got us more than we need here, but we can't really adjust this one because it'll affect that one. So let's see if the second one will help us with this one. All right, the second one has water on the wrong side. It has water over on the right hand side. We need it on the left hand side. And so if we write the other one reversed, excuse me. And then we put these terms on this side. And yes, oxygen. That side. That gives us more water than we need. So we need to take half of that one. But in doing so, what we've done is by flipping the equation, what does that do to the K? We have to invert it. And we have to take the inverse of that K. So the K here is going to be 1 over 1.8 times 10 to the 37. Okay. We'll resolve that in a minute. But the next thing we need to do is take half of this one. What does that do to the K? If we take half of the K, that's square root, yes. So for this one down here, this is going to be the square root of 1 over 1.8 times 10 to the 37 is going to be the K for this reaction once we've adjusted it. Half of the hydrogens and half of the oxygens. Okay. All right. So that gives us this one. Let's do this one. Gives us that one. It gives us this one. And this one cancels and leaves us with half of this one. And this one cancels all of that one. Okay. So when we add them together, we get this equation. And so what's the K for that equation? That's the question. Well, we have to multiply the K's together, don't we? We multiply this K times that K to get the overall K for this one. Okay? So let's crunch some numbers. Let's see, 1.8 exponent 37. I'm going to take the inverse of that and then take the square root of it. Okay, so that's, I'll write it down here. This one resolved will be 2.36 times 10 to the minus 19. Then that one is times this one. 2.3 exponent 6 times. So this value is going to be, oops, this is going to be 5.4, round it off, times 10 to the minus 13. There we go. So now we've got our K, we can use, to find this one, we can use this equation right here. So delta G0 equals negative R, which is 8.3145 joules per mole K. And temperature is already in Kelvin, 600.1 K. And then the log, natural log of this value, K for the equation. And that's 13. There we go. So let's see, I've already got that one in, got this one in, so I'll take the natural log of it, and then we'll multiply it by 600.1, and then multiply that times 8.3145. Yes. So that gives me 1.4 times 10 to the 5th joules. Right? Usually free energies and enthalpies are in kilojoules, simply because they're just huge numbers. And entropies are usually in joules. Okay? So the answer is given in kilojoules. We need to take kilojoules out of this. All right. What's a kilo out of this one? Well, it would be kilojoules. We would remove 10 to the 3rd out of that, right? So we'd have left over 10 squared. All right. but it's in standard notation. So let's move the decimal over to the right. Let's see, I left out, could put a one, we rounded it to that many places. Problem is, we've only got two significant figures working out here. Right, so pick the best answer, right? That's 141 kilojoules. Since we don't have one that says none of the above, then your best answer is 141.
Up there, 141.
Yeah. Yeah, I added this one in here, but technically I'm only permitted two significant figures. Right? Because all these values, that one has 4 in it, but these only have 2. So I should only have 140 would be the proper. But 141 is your best answer out of that choice. Okay, 53 coming up. Okay. Get my bearings here. Okay. Let's make some room. That's at 53. All right. So we've got this reaction where nitrogen dioxide the proper term for that is dimerizes. In other words, you get one of these attached to another one, so that's where the dye comes from, and it gives us into 4 gas. Let's see, delta H0, put it over here, is a negative, let's see it better, 56.8. 6.8 kilojoules. Delta S0 should be in joules. Minus 175. Should have a negative there. Yes. Let's back this up a little. Negative. A negative 175 joules per K. In a container at 298 K, so we're given the temperature also. 298 K. And they're mixed together with an initial pressure of 2.4 atmospheres and 0.42. All right, see how that's read in a container. N2O4 is the first one, so it's 2.4 atmospheres. Right? They're listed backwards from the way the equation is written. So that's a point of possible mistake. And a partial pressure of 0.42 for the NO2. These are initial pressures. All right. So is that everything we're given? Which of the following statements is correct? Some N2O4 will decompose into NO2. Some NO2 will dimerize to N2O4. System is at equilibrium. Final total pressure must be known to answer the question. Okay. So if this is the initial, we could calculate a Q value for this. Right? All we have is the expression here would be Q equals N. Actually, that's not right because it's in partial pressures. Would be P N2O4 divided by P NO2 squared. Right, so we can calculate Q. Whether we need it or not is another question. So that would be 2.4 divided by 0.42 squared. Or here, 0.42, let's square that one. Divided. So this would be 13.6 would be the Q for that. Now, if we can determine the K for this reaction using this information, we can compare the K to the Q and see which way it's going to go. Okay. So, what do we have available for us? Well, let's see. We got delta H and delta S together, but we don't have delta G. All right, so we need something else. How about this one? This one actually has K in it. And there's delta H, there's delta S, R, T. Oh, we got everything we need right here. Okay, so the natural log of K equals delta H 0 over R 1 over T plus delta S 0 over R. So, so let's do get in the way. Log K then would be negative, and this should be the R is 8.3145 joules for a mole K. So this needs to be in joules. So this would be minus 56.8 times 10 to the third joules. Okay. I just took that K and turned it into 10 to the third. Excuse me. And then the R is 8.3145. And then we have 1 over temperature, which is 298. Okay. And then we have, I don't have to bring it down here. Delta S0 is here, minus 175 joules per K divided by 8.345. Okay, so this term goes right here. And that'll give us log K. And we just need to solve that part of the equation. Okay. Excuse me. 56 exponent 3. Let's see, let me back up. 56, change the sign. Oh no. That's a negative times a negative is positive. So I can leave it alone. Okay. Enter. 8.3145 divided into that, and then divide this into it also. 298. So that's 22.6 for this term. So what's this term? This is a negative term. 175 enter and 8.3145 divide. This is 21.0. This is 22.6. And this is a negative 21.0. So I just need to subtract those two. And this gives me log K 1.554. Keep a few decimals. Now this is where we need to take the anti-log of 1.554, which would be K would be equal to E to the 1.554. So there's my key, E to the X. And this gives me 4.7 is K. All right. So we know what K is, we know what Q is. Which way is the reaction going to move? Right? If Q is bigger than K, that means we've got too much over here. This is too big for that to be bigger than K. So it's going to move that way. Okay. Okay. So we're going to produce NO2. Some N2O4 will decompose into NO2. That's it. Hey. That was a lot of work to answer a simple question. Everybody okay so far? Okay. It's 53. Let's see. All right. Scoot down to 56. Okay. It appears that this one should be easily solved with Le Chatelier's. So we have this system at equilibrium. PCl3, I bet it's got chlorine gas. Yeah. Actually, it should be a double barbed arrow because it's equilibrium. PCl5. Okay. Delta H, 0, standard conditions at 25 degrees. Yes, those are standard conditions. Equals 92.5 minus 92.5 kilojoules. Okay. If the temperature of the system is raised, what happens to the ratio of PCl5 to PCl3? And we're looking at what happens to this ratio. PCl5 to pressure. Be consistent here. What happens to this ratio, PCl5 to PCl3, correct? Yeah. What happens to that ratio? Well, this tells us that it's exothermic, correct? So that means the heat goes on this side. So if the temperature of the system is raised, it's going to drive this reaction backwards. Right? It's going to make less of that and more of that. So the ratio decreases. So that's what the answer would be. Let's see who's next. 58. Move this one. I've got a note there to go to version 256. That's, yeah, version 256 is based on the same information. So we're going to go from here, do this one, and then we're going to skip over to version 256 so I don't have to write it up there again. And then we'll come back if need be. See, do we need to come back? H. Yeah, we will have to come back. Okay. So we're on version 158. All right. So we've got an equilibrium constant Kp in atmospheres for the dissociation of chlorine into 2-Cl atoms, measured as a function of temperature in K. All right. So what are we looking at here? If we're doing the if we're measuring the K at different temperatures, then we're in this region right here. We got K versus temperature, correct? So for this reaction, I'll just write it up here for fun. Oops. 2Cl, there we go. And those are gases, of course. All right, if we plot this against 1/T and log K here, we should get a negative slope. And we're told that that equation here looks like this. It has a slope of minus 1.651 times 10 to the 4th. This is the slope right here. log K equals, with a negative slope, negative 1.651 times 10 to the fourth there. And that's times 1 over t. And then, does it give us a y-intercept? Yeah, y-intercept of 14.51. So this, where it intercepts here, is 14.51. But the slope is equal to negative 1.651 times 10 to the fourth. And this right here is equal to negative delta H 0 over R. Okay, the answers are couched in terms of exothermic, endothermic. Well, we can say C, reaction rate is high. You can't tell reaction rate from this because we're talking equilibrium. Reaction rate is kinetics. And so the rate is immaterial. The reaction is not spontaneous. Now I can't say anything about that yet. We can determine delta H 0. Right? Yeah, we can do that because we know that this value is equal to this value. 4 times 10 to the fourth. Right? So we throw away the negative signs, and that means delta H 0 equals 1.651 times 10 to the fourth times R, 8.3145. And this is going to be in joules. Well, the reaction is exothermic, endothermic. This is a positive value, isn't it? Right. So it's endothermic. Right? E says none of these, and we found one that's right. Now, D, the reaction is not spontaneous. We can't tell that from the data because we only have access to delta H. We don't have any indication of entropy or free energy. Right? If we had some way to solve for free energy, then we could do that one. You know what? At what temperature? Doesn't say. We could determine whether it's spontaneous or not if we know the temperature. But we've got lots of different temperatures here. If we could plug in a temperature, like we fill this in, if we could put a temperature value there, we could find out what K is. Right? Then we could put K in here at that temperature and find out what delta G is. But we can't do that because we don't know what the temperature is. So it's several temperatures. All right, so the best answer here is endothermic. It's a positive delta H. All right, so let me leave that alone because I need to go to version 2, number 56. And we'll come back. What page is this? 14. We'll come back to page 14. Number 2, 56. And here we are. Okay. So temporarily, I'll just change this to this and that. That's not chapter. That should be version 2. Chapter 17, that's version 2. And this is 56. Okay. We're looking at the same reaction. We've got the same values here and there. 1, the value of delta H for this dissociation. Okay, we just go ahead and complete this calculation then and find out what the delta H is. 1.651 exponent 4 times 8.3145. Okay. So this is 1.373, say, times 10 to the 5th joules. It's in kilojoules, isn't it? Okay. So this needs to be 10 to the 2nd kilojoules, which moves this decimal over to 137 kilojoules. So B is the best answer to that one. Okay, I could have kept this one, I guess. Okay. So now we'll go back. We can go back to version 1 and finish out the, I think it's the last one in version 1. Let's say page 14. Come on. Wakey, wakey. Not respond. There it goes. Okay, we did that one. We did that. Okay, that's it. Now 59. Here we go. 59, version 1. Not chapter 1, version 1. Okay. A certain process, apparently it doesn't matter what it is, at 300 K, temperature equals 300 K. And delta G is, this is the actual delta G, right? Well, that's obvious because this is not a standard temperature. So the actual delta G for this process is minus 10.4 kilojoules. And the delta H is minus 7.0 kilojoules. Okay. If the process is carried out reversibly, what does that mean? Reversibility is theoretical. The only way that you can have a reversible process is if the increment of change is infinitesimally small. It's where you can just kind of wiggle back and forth between forward and reverse reaction. Right? That's the ideal situation. Most reactions are irreversible in one direction. Thermodynamically speaking, like, that's not to say that your equilibrium will not promote a reverse reaction, right? That's kinetics anyway. Okay, so now that we have this information, if it's carried out reversibly, the amount of useful work that can be performed is what? Right? The amount of useful work, the maximum amount of useful work is equal to what? It's equal to Gibbs free energy, isn't it? The maximum amount of work, useful work, that can be performed is, and it's spontaneous if delta G is negative. So the maximum amount of work that can be performed is negative 10.4 kilojoules. Okay, so that's D. Looks like it was going to be hard, but you tease out the information and go to the question, and it's simple. That one was really simple. Let's see, 59. Okay, now we're into version 2 from the beginning. All right. At number 2. Okay. All right. This problem, number 2, would be easier if you've had statistics or at least an introduction to probability. But I'm going to try to show it to you the long way first and then the short way. We have 2 bulk flasks containing 5 particles. We've got this one connected to another one. And there are 5 particles in there, A, B, C, D, and E. What's the probability of finding all 5 particles on the left side? Well, what's the probability of finding, say, A on one side? Right? It's either going to be over here or over here, right? So it's 1/2. Yeah, it's 1/2 probability, right? What's the probability of also finding B over here? Well, it's 1/2 also. Right? C, D, and E. So that's the probability of finding all of them on this side. So what is that? Well, that's 1 times 2 to the 5th power. Or, let's see. Second power would be 4, 8, 16, 32. 1/32. Well, we've got it in percentage value, so we have to find out what that fraction means. So let's take 32 and invert it and then times 100. That gives us percent. 3.125. Or 3.13%. Okay. So this is a permutation. Right. How many choices do you have? You have 2. Either one. Right. If you got 5 particles, then you do that 5 times. So there you go. Since I'm not a math scholar, that's as far as I take it. I just learned how to use it. Let's see. Skip a bunch. There, 14. 14. For the process, what in the world is that? That's trichloromethane. Ooh, solid. This must be cold. What's the melting point? Yeah. Because trichloromethane, as I know it, is I think it's a liquid at room temperature. Let's see. Oh, and it's going to the liquid. PHCl3, liquid, that process. Delta H is 9.19 kilojoules per mole. And delta S is 43.9 joules per mole K. But we only got 1 mole of each, so we just throw them all out. What's the melting point of chloroform? Oh, that's the other name for it, excuse me. Trichloromethane is proper. Chloroform is probably more commonly known. Used to use it in the operating room. Chloroform and ether. I have the mask and the one person, all they would do was just drip the stuff on the mask so you can breathe it in and knock you out. Let's see, where am I? 14. Okay. Oh, we've done one of these before, right? If this is a melting point, it's at equilibrium, which means we're looking at the system here. And the system is going to be delta H0 over T. And these values are always relative to the system. If you're not told its surroundings are total, it's always system. So that means we have delta S0 for the system equals delta H0 temperature. So we're solving for the melting point is equal to delta H0 over delta S0. So all we have to do is be sure our units are correct. This one needs to be changed to joules. So it's 9.19 times 10 to the third joules. And this one we can leave it just like it is. Joules per K. 9.19 x3. This is 209. Okay. And of course it's in centigrade, Celsius. So I need to subtract 273 from that, which is minus 64 degrees C. So yeah, that's it's going to have to be really cold to be a solid at minus 64 degrees. So at room temperature, it's probably a liquid. All right, that was 14. Okay, let me check. Oh, we're good. Okay, scroll to the next one. Number 20. In which case must a reaction be spontaneous at all temperatures? Okay. This, we had a slide in our lecture on this one, and it used this formula right here. Delta G equals delta H minus T delta S. So if it's spontaneous at all temperatures, that means this has to be negative. So what would give us a guaranteed negative here? Well, that one would be negative. This one would be positive. Because any positive value here times negative, 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 negative. So delta H is negative and delta S is positive. That's it, D. Okay. 20. Let's see. Let's see, 26. When a stable diatomic molecule spontaneously forms from its atoms, the diatomic molecule, let's just say A, spontaneously forms from its atoms to A. So that's the process. And spontaneous means it's going from here to there. What are the signs of delta H, delta S, delta G? Delta H, let's see. Second one is delta S. Well, we're not saying it's standard conditions, so it doesn't matter. Delta G. Under whatever conditions they want to give us. Well, no, it is 0. 0. Just the answers don't have zeros on them. All right. If it's spontaneous, right, we know that this one is that. The delta S we have to deduce from the fact that we're going from 2 to 1. So this is becoming smaller. Right, we're going from this disorder to that order. And delta H, that was a little trickier. if we're going from this one to that one, this one means that it's at lower energy, right? Yeah, this is higher energy. This is higher energy, and this is lower energy. It's more stable. This is more stable than that one. So it might help to draw a picture and progress of the reaction. All right. If the reactants have higher energy and the products have lower energy because they're more stable, then our graph looks like this. So what does that mean? That means that this is an exothermic reaction. Right? Because it's final minus initial. So final E minus initial E, this one's low, this one's high, minus the high makes it a negative, which is exothermic. So this one's also negative. Okay. I'll take that as a yes. All right. 26, and who's next? 31. All right. So the KSP for salt, sodium chloride. Remember what KSP is? Solubility product. So we say sodium chloride is going to sodium ions in solution plus chloride ions in solution. And I guess we can say this. Put it in solution, then it's going to have a KSP value, which I don't know if we'll need these, but it would be this times this. Right? That would be the expression. So we're given delta G values, and they're looking for K. So do we have a formula over here that incorporates the delta G's and the K's together? This one right here. Right. We can find K, and this is at 25 degrees. Okay, so we know the temperature, and we can find the delta G. We can get the delta G from the table. Okay. Oh, they're saying this is solid. So it's solid here, and it's going into solution there. Okay, that's valid. So what would the delta G for this reaction be? It would be sodium, right? Minus 262. And that's kilojoules. Plus chlorine, which is minus 131 kilojoules. And then subtract the formation for sodium chloride, which is a minus 383.8 kilojoules. Okay. All right. So we can calculate delta G zero here. Just need my calculator. All right, 262, change the sign, and then a minus 131. And then this is a minus times a minus, so that's add 383.8. And this is minus 9.2 kilojoules. All right. So now we can find out what KSP is with this equation. This value here, and we're going to have to change the units because R is in units of joules. So we got to change this one. Minus 9.2 times 10 to the third joules. Okay. So now, delta G right in the middle here. Minus 9.2 times 10 to the third joules equals minus R, 8.3145 times temperature, 25 plus 273, right? Has to be in Kelvin. And then times log KSP. Okay? So these are all multiplied, so we just need to multiply these together, divide them into that. Yeah, I'll drag it out so every step will be here. 10 to the third divided by minus 8.3145 times 298. Okay. So there's the value of log K. This is a minus, that's a minus, so our answer is going to be positive. 9.2 x 0.3, 8.3145 divided and 298 divided. So this is 3.713. Okay. And the KSP is what? It's E to the 3.713, which is about 41. A. Okay, so it's extremely high, which is what would affect, right? Sodium chloride is very soluble in water, so it has an extremely high KSP. All right, it's 31. 34. Or have we done this one already? Is this the one that well, that was 50 something one. This how will raising the temperature affect the? This one looks awful familiar.
Yeah, no, when I think the saw and the sense temperature.
Yes, thank you. Yeah, you're right. It's the same system with a different question. All right, so NO gas plus 1/2 oxygen, yeah, equilibrium with NO2 gas. Yep. And delta H0 is minus 56.91 kilojoules. K is equal to 1.46 times 10 to the 6th at 25 degrees. Okay. How will raising the temperature affect the amount of NO? Oh, all right. So this is an exothermic reaction, right? Which means we put delta H over here. It evolves heat. So raising the temperature would add to this side. Le Chatelier said it's going back this way. So the amount of NO will increase. Oh, that's it. Yeah. That was simple enough. All right. 34. Let's see here. How about 40? 40 is definitional. Actually, I've seen the definition of second law of thermodynamics in various forms. So, what does the second law of thermodynamics say? Well, in its simplest form, it says the entropy of the universe, and that is the universe, is always greater than 0. Entropy is always increasing. for the whole universe. But I think these potential answers are worded a little differently. E says none. All right. Energy is conserved in a spontaneous process. What's that one? No. That's the first law. Energy is always conserved in a reaction, in any process, physical or chemical. All right, so it's not A. B, the entropy of the universe increases during spontaneous, that's it. Entropy always increases in a spontaneous process. The heat content of the universe increases. No, that's the false first law, right? Right? That's wrong. All of these are valid components of the second law. So just this one only has to do with entropy. All right. 43. Can I get the whole thing? Yeah, I can get the whole thing on there. 43. A mixture of hydrogen and chlorine remains unreacted until it's exposed to ultraviolet light. So we've got 42. We've got hydrogen gas and chlorine gas that are in a flask with it's either a clear flask or a peephole flask, so that you can shine ultraviolet light through there. And the ultraviolet light does what? It provides the activation energy for the reaction. So as long as it sits there in that flask, just like that, well, we don't know yet, based on the information. I haven't put everything up here yet. It's going to make 2 HCl gas. Now, if we say delta G for this reaction is negative 4554 kilojoules, delta H is negative 44.12 kilojoules, and delta S is minus 4.76 joules. Okay. Now we can say a little more about the reaction. Right? It is spontaneous from left to right. It will go from left to right eventually, but maybe not in our lifetime, right? So we've got two things going on here. One is the equilibrium, which says, yeah, it's spontaneous from left to right, but until we shine the ultraviolet light on it by what? Burning a magnesium strip. Right? That's why when you burn magnesium, don't look at it, right? Unless you like this way up there. It'll burn holes in your retina. But until we provide enough activation energy, then the reaction won't go in our lifetime. Right? So that's kinetics, whereas this is equilibrium. Okay, now let's see. What's the question? Which of the following is consistent with this information? All right. How about A? The reactants are thermodynamically more stable than the products. The reactants are no. If it's spontaneous, this side is more stable. Right? The products are more stable if it's spontaneous from left to right. So that one's wrong. How about B? The reaction has a small equilibrium constant. Well, how do we find that? Find the equilibrium constant. 42. Let me see, did I actually calculate that? Yeah, I did. Okay. Small equilibrium constant. So if delta G 0 equals, is this at 25 degrees? I'm going to say we have to assume equals minus RT log K. Right, so this one is minus 4554 times 10 to the third joules. And this is minus 8.3145. And temperature, we would have to say is 298 K. That's the only way we can solve it. That's log K. Then the log K is going to be that times that divided into this. So 45.54 exponent 3. Just change that sign. And then 8.3145 here, change that sign. 298 times. Let's see. It's 0.554 times 10 to the fourth. It's this number. And divided by this product, 2.478 times 10 to the third. There we go. So let's do this. 4.55. 4. There we go. So that's 5 minus 2. That doesn't make any sense. Let me do that again. Did I do that right? Yeah, that's right. 8 times 3 is 247. This one might be wrong. You can do that again. 8.3145. 298 times. And that's right. And then 4.554 exponent 4. That's, yeah, this is big. 18.4. That's 370. 8. So K is going to be e to the 18.38, which is 9.6 times 10 to the 7. Okay, so B, the reaction has a small equilibrium constant. No, it's got a huge equilibrium constant. How about C? The ultraviolet light raises the temperature of the system and makes the reaction more favorable. Does it? No, there's no heat transferred into that vessel. It's all light. Now, you could argue that some of that light might be converted into heat, right? It activates things, but for the most part, that ultraviolet light doesn't raise the temperature of the system. Besides that, it doesn't make the reaction more favorable because this is its favorability regardless of what we do. Right? Yeah, I guess you could argue this one. But that's not the best answer. It's possible. The negative value of delta S slows down the reaction. What's wrong with that question? That's kinetics. It's trying to move entropy over to kinetics, and you can't do it. This is thermodynamics. This is a state function. So the reaction rate doesn't change based on any of this information. So C and D, C maybe, D definitely not. How about E? The reaction is spontaneous, yes, spontaneous, but the reactants are kinetically stable, yes. They're not going to go very fast until we introduce some activation energy. So if we drew that in a picture, right, energy is here and progress there, right, it would be exothermic. So it'd be like this, here, here. But this would be a huge activation energy. that means it's kinetically stable. It's going to stay here unless we pump it with some energy to get it over that hump. Okay, so C is questionable, but E is the better answer. That's 42. And scroll. 52. Here we go. All right. Yeah, I guess I got time to draw that. 52. So here we've got a graph of 1 over t, right? And log k. And right here is the y-intercept at 3. And out here, 0.20 is the x-intercept, actually. It goes down like that there. Okay. Question is, what is delta S 0 for the reaction? Okay, so we're looking at this plot right here. Log k of the y. This one is the slope, right? This one is the x value. And this one is delta S 0 over r. This one is the y-intercept. The y-intercept is 3. So 3 is equal to delta S 0 over r, which is 8.3145. So delta S would be 8.315 times 3. I should be able to do that. 3. So 24.9 or 25, rounded off, 25. There you go. So the answer is C. Okay, that's graph interpretation. Right, 52 is the next one we've already done. Yes, I think we came to that one earlier, so we're going to go to 57 now. 57. All right. For a certain process at 300 K, temperature equals 3. Let's start to look familiar too. Oh, okay. Yeah, it's kind of a tricky question. So let's go ahead and do it. Delta G in these circumstances is minus 12.2 kilojoules. And delta H is minus 7 kilojoules. If the process is carried out so that no useful work is performed, we're not getting any useful work out of it at all for this process. What's delta G? It's the same, yeah, right. Whether or not you get work out of it is immaterial. This is the maximum amount of work that you can get. Delta G doesn't change. Okay. Now the work, the actual work, is 0. You're not getting any work out of it, but the delta G is still minus 12.2 kilojoules. Kind of tricky. All right. Oh, that's it. Right? That's the last one. The last one I had on my list. Now, if you guys have questions about others, then there's plenty of time. We can look at them. Otherwise, I'll see you back on Tuesday.